Okay, here in example 3, we're going to solve the inequality using a sign chart. So I have 2x minus 1, all multiplied by the quantity square root of x plus 4. And the first thing that I notice is that because I have that square root in here, I'm going to have some domain restrictions, namely that x plus 4 has to be greater than or equal to 0 because it's a radical. And so therefore, x has to be greater than or equal to negative 4. And so when I draw my sign chart, I'm going to have negative 4 here, and I'm not going to check anything to the left of negative 4. Now, one more thing is that when you look at this inequality, we are looking for the sections that are strictly negative, not the zeros, just the negatives. And so therefore, negative 4 is a 0, and therefore this is going to need to be an open circle at negative 4. Anything to the left of negative 4 is going to be undefined because of the domain restriction, and then I'm going to go ahead and find my other 0 from this other factor right here. So 2x minus 1 is equal to 0, means that x is going to equal to 1/2, and since that is a 0, and we're not going to include the zeros here, I'm going to make that an open circle as well. Okay, so now I'm ready to start plugging in test values from each interval into the function. And so from the first interval, if I choose 0, then 2 times 0 minus 1 is going to give me negative 1. So I'm going to put a negative there. And into the second thing, I'm going to get the square root of 0 plus 4, which is going to be positive, and a negative times a positive is going to be negative. If I plug in something bigger than 1/2, like 1, I'm going to get 2 times 1, which is 2, minus 1 is positive, and square root of 5, which is also positive, and so that is going to be a positive section. Now, look back at your inequality symbol. Because it says less than 0, we're looking for the negative sections. We are not going to include the zeros, and so the only thing a part of our answer is this interval right here, from not including negative 4 until not including positive 1/2. Okay, in letter B, we have 3x plus 5 squared multiplied by the absolute value of x minus 2. And so if we start with the first factor, I'm going to have 3x plus 5 is equal to 0. And so that tells me that x is going to equal to negative 5/3, and that is going to go on my number line over here. And because we are including the zeros in this particular problem as opposed to example A, that's going to be a filled in circle so that I know to include that in my answer. Okay, the other factor is absolute value of x minus 2, so if you just take what's on the inside there, you're going to get x is equal to 2 as the other 0, and again, since we're including the zeros, I'm going to put a closed circle. Now, here's the thing about this problem. If you look at the first factor, it is a quantity that is being squared. That is going to always result in a positive. This is an absolute value. Absolute value is always positive. And so this function is always going to be positive or 0. And so we already know where it's going to equal to 0 at negative 5/3 and 2. It's going to be positive everywhere else. And so when we are looking for the intervals or the values of x, I should really say, where the function is either negative or 0, this function is never negative, but it is 0 at exactly 2 values of x. And so my answer here is going to be the set of two numbers, negative 5/3 and comma 2. Okay, letter C is a rational inequality because we have a rational function and we want to know where that rational function is either positive or equal to 0. Now, for rational functions, I know that I have domain restrictions, and so the domain restrictions are going to come whenever the denominator is equal to 0. So I'm going to get x cannot equal to 0 and x plus 3 cannot equal to 0, which means that x cannot equal to negative 3. Now, I'm also going to have some zeros to put on my number line, and zeros will always come from the numerator. Okay, domain restrictions are from the denominator, we already know that, but the zeros come from the numerator. And so if I set the numerator equal to 0, I'm going to get x is equal to 5. And so when I go to draw my number line, I'm not only going to put the zeros on my number line, and we are going to be including the zeros in this particular example because of the inequality sign saying greater than or equal to 0 right there. But I'm also going to put the domain restrictions. Make sure you put them on the number line in order, -3 first, and then 0. And domain restrictions are never included. So I'm going to put that here as a note underneath the domain restrictions that these guys are never included in your answer. So they are always going to be open circles on your number line. So that's why they're open even though the problem says greater than or equal to 0. Okay, so we are ready to start testing some values. I'm going to take a different color here. For this first section, I'm going to put -4. Now, -4 minus 5, plugging into the numerator, is negative. But when I raise it to the 4th power, that turns it back to positive. In the denominator, I've got -4 as an x right there. That's going to obviously be negative. And then -4 plus 3 is negative, and 2 negatives are going to turn that back to be a positive. Now, between -3 and 0, you've got some options as to what you can plug in. I'm going to plug in -2. -2 minus 5 is negative, but when I raise it to the 4th, that moves it back to positive. -2 is obviously negative, and then -2 plus 3 is a positive, and 1 negative is going to result in a negative. Between 0 and 5, I'm just going to choose 1. 1 minus 5 is negative, but when I raise it to the 4th, it becomes positive. 1 is also positive, and 1 plus 3 is positive, so that section is going to be positive. And then finally, we have from 5 to infinity, we could choose 6, and notice that all 3 of those are going to be positive again, which is going to give me another positive section. So, going back to the inequality symbol, we're looking for all of the positives and zeros, and so I'm going to have this first section, which is represented by -infinity to -3, not included, because again, remember, this was a domain restriction, so was this, which means we wouldn't include 0 either. And then the other positive section is going to start at 0. It's going to go through 5, since we were going to include 5 as a 0, and go all the way to infinity. So that will say 0 to infinity, and that will be the answer to this particular question. Now, I want to play the what-if game just real quick. If this inequality said greater than 0 and not equal to 0, I then would have to exclude 5, which means I would still have -infinity to -3, just like before, but then I would have to separate this second part into 2 separate intervals. So I would have to go from 0 to 5 and not include 5, and then go from 5 to infinity. So again, the question didn't ask you to answer that question, but I just wanted to play the what-if game and show you what if this question had said greater but not equal to 0, then this would have been what your answer would have looked like. Okay, we have a problem in example D here, and that problem is that we have a term that's not a fraction, the x squared, and we have a term that is a fraction, the 2 over x, and we need to combine these terms and actually subtract them so that we get one rational function and not these 2 terms that don't look anything alike. And so I'm going to show you that process here over on the side. Remember that x squared could really just be written as x squared minus 1, over 1 minus 2 over x is greater than 0, and my objective here is to get a common denominator, and the common denominator is just going to be the product of these 2 denominators, 1 and x. And so if I multiply 1 and x, this is going to give me x. And now I need to multiply these fractions by something in order for them to also have a denominator of x. And so if I look at the first term, the denominator right now is 1, and so to get that to be x, I need to multiply by x. But if I do that in the denominator, I've got to also do it in the numerator. And so now when I multiply those numerators, x times x squared becomes x cubed. Now the second fraction already has x as its denominator, so there's nothing that it needs to be multiplied by. It's just going to stay minus 2. And now this question looks a lot better, and it looks very similar to example C, in fact. And so remember, on example C, we did two things. We found our zeros, which came from the numerator, and our domain restrictions, which came from the denominator. So our domain restriction in the denominator is that x cannot equal to 0, and in the numerator, we're going to get our 0 by setting equal to 0. I'm going to do this over here just because I'm a little bit out of space over there on the left. Okay, add 2 to both sides, and then to get rid of a cube, I'm going to take the cube root. And so x is going to equal to the cube root of 2. And so on my number line, I am going to have 0. It is not going to be included because as a domain restriction, it is never going to be included. Domain restrictions are never included in our answer. And then the cube root of 2 is a 0. Looking back up here at the inequality symbol, we're not including zeros on this particular problem. So I'm going to put an open circle there above cube root of 2. Now, when I plug in, I'm going to plug in to this simplified version right here. So be very careful to do that. I'm going to start by plugging in a negative number. So let's just say, for example, -1 would be a good choice. If I plug in -1 for x in the numerator, -1 cubed is -1, minus 2 becomes more negative, so that's going to be a negative. And in the denominator, we're going to plug in a -1, which is going to make that negative, and so therefore that will be a positive section. In the middle, between 0 and cube root of 2, I don't exactly know what cube root of 2 is, but I know that it's bigger than cube root of 1, and cube root of 1 is 1, and so I can use 1 as a test number here, and if I plug it into the numerator, 1 cubed minus 2 is negative, and the denominator is going to be positive, and a negative divided by a positive is negative. And now, cube root of 2, again, I don't know what that is, but I do know that it's smaller than cube root of 8, and I know that cube root of 8 is 2. And so I can safely plug in 2 to the numerator. I'm going to get 2 cubed is 8, minus 2 is positive, and divided by 2 is also positive, so this will be a positive section as well. And therefore, looking back again at my inequality symbol, I'm looking for the positive sections, and so that's going to be here from -infinity to not including 0, and the other positive section here, which is from, in this case, not including cube root of 2 until positive infinity. Okay, last one, and then we're finished with section 2.8. In the numerator, the first thing I want to do is I want to factor if possible. And so I see that in the numerator I can take out an x, and that's going to leave me with x squared minus 4 all over x squared plus 2 less than or equal to 0. And then what I notice is that I can factor again because of the difference of 2 squares. So x plus 2, x minus 2 over x squared plus 2 is less than or equal to 0. Now, my zeros come from the numerator, so if I set the numerator equal to 0, I'm going to get 3 zeros, 0, -2, and +2. And domain restrictions come from the denominator, not equaling to 0. And so what am I going to get here? X squared cannot equal to -2, so x cannot equal to the square root of 2i, which is not a real number, and so therefore on my number line I'm not going to have any domain restrictions, but I am going to have zeros at -2, at 0, and at 2. And looking back at the inequality symbol, this says that I am going to include the zeros in my answer. So I'm going to go ahead and fill in circles above each of those zeros, and now I'm going to start testing values. So on the first interval I could try -3. Plugging into the numerator, -3 is negative, -3 plus 2 is negative, and negative 3 minus 2 is negative, so that's 3 negatives in the numerator. And in the denominator, let's just think for a second. If I have some number squared and then add 2 to it, that is always going to be a positive. So in that denominator, I'm just going to go ahead and put positive for all of those, and then really the only thing that's going to matter is the numerator. So 3 negatives in this first section, that means I'm going to have a negative. In the second section, I'm going to plug in negative 1. I already know the denominator will be positive, but in the numerator, I'm going to have a negative, a positive, and a negative. And so 2 total negatives means I'm going to result in a positive. Between 0 and 2, I'm going to try 1. 1 is positive. 1 plus 2 is positive. 1 minus 2 is negative. The denominator we know is already positive. And so therefore with 1 negative, that section is going to be negative. And then finally from 2 to infinity, I can plug in, let's say 3. 3 is positive, 3 plus 2 is positive, 3 minus 2 is positive, the denominator is positive, and so that's going to be positive. And so going one more time back to our inequality sign, this says we want the negatives and the zeros, and so this is going to be negative infinity to negative 2, with a bracket since we are including that 0, and from 0 to 2, and we are going to include both of those zeros so that we get this as an answer. Okay, any questions on section 2.8, please feel free to reach out. You guys have a nice day.